So, very good morning to all of you. And I'm Prachi Pasalkar from Pune Knowledge Cluster. And I welcome you all for this fifth session of this course. Today we have with us Mr. Amogh Tarkar, and he is a machine learning researcher in AI Research Lab at Persistence, and currently is exploring private preserving machine learning techniques. In his role, he explores the potential of latest machine learning techniques and helps to transform ideas into solutions. So we are very happy to have you here today for the session, and over to you.
Thanks, Prachi, for this kind introduction. And I welcome everyone who joined us. I know the times are difficult, but still you guys have joined in for a live session, and that's wonderful. So without any more ado, let's get started. So yeah, here is the crew from Persistent who has been interacting with you. So we are through the fifth session today. So over the course, we have been discussing about interpretable AI, fairness, and now we are on this journey towards privacy preserving AI. And this is a first session in a kind of series of three. So there'll be around three privacy preserving related sessions. Today is the first one. I'll be following up on 10th as well on a second one with which we'll go a little bit deeper than what we'll discuss today. And then on 6th, there'll be Sneh Kumar talking very specifically about differential privacy. Yeah, so before we start, a quick disclaimer. These thoughts are mine and not directly belong to my employer. All right, so here's a quick agenda. We will talk about what is federated learning. We will then go into what are applications of federated learning. I also plan to show a small demo of how to basically a code walkthrough of federated learning, and then we can take question answers, and we will have a couple of breaks in between as well. Uh, so let's get started. So let's try to understand like the overall pillars of responsible AI, which we have been discussing throughout these sessions. So these are the pillars on which responsible AI can be built. So reproducible is something which needs to be like there needs to be a pipeline which has to be reproducible so that everything is standardized and we can get to that specific version very quickly. Accountable is something wherein we have these various like fairness and all those kind of studies, and also it's sort of human in the loop so that it's not completely like going in the way the data is saying. So if there is bias, we need to take care of that. Then transparent as in it needs to be interpretable, explainable, and those are covered in the other section. So we are now coming towards this pillar, which is talking about what is private machine learning, and in that let's take a deep dive on what is federated learning and how exactly does it help to keep this particular the data as private. So let's just to just understand this idea, let's try to imagine that we are a company which is a startup, and our main goal is to actually build the best credit card fraud prevention consulting firm in the world. So we are not directly with the banks, we are independent, and what we want to do is that we want to be this group which can actually tell you all sorts of what are all sorts of credit card frauds which are possible, and we can basically consult on how to prevent it. And of course we will be using machine learning for doing it, right? So the goal is to basically the goal is to not learn about each and every transaction, but actually be this consulting firm which knows everything from all sorts of banks, not just one type of a bank. And we want to be the best in the world, so we want to just scale from one country to another, and all income groups and so on. So that's basically the big startup idea we have. And we want to really get to that part wherein we are the consultants for the world, wherein anybody can ask us any sorts of questions about credit card fraud, and we should be able to at least give them a good answer for that, right? So with that sort of a very tall goal of building such a model, we try to try to apply machine learning in the standard way, wherein we would need to go out, get some curated labeled data, put it all together in a single data center, hold lots and lots of data, and perhaps purchase it, perhaps you know, partner with companies, just get all this data in one place. And once it is there in one place, then we start uh, training multiple ML models to actually help us identify these various patterns which are observed across all these various banks. Right? So that's our kind of high level strategy of like, let's use machine learning and AI to solve this problem of like preventing fraud transactions with credit cards. So that's what our goal plan was. And so what we do is that we go to these banks and we are like, we want your data. We are not directly working with only one bank, but we are working with multiple banks. And to build our model, which will help all these banks, we basically just go ahead and we ask data from each and every bank. So the question is, will these banks share their data? It's definitely their data about their customers, and it could have a lot of PII, personally identifiable information. There could be some sort of competitive advantage about their data, which they are like, suppose there's a bank which has like gathered, like it has say 10 lakh customers, and another bank which has 1 lakh customers. All these customers are basically what that banks have struggled to get there, and the data which they have collected actually belongs to them as such, and they will not easily share this data with any third parties like the way we are, right? So like potentially what each bank would do is that they'll try to build their own fraud detection model and go on. But when a consulting firm like the one we are building comes to them, they'll clearly just say, we are not giving you the data. Try to find alternatives to get there. So what we need to do is that we think about it, and then this is one idea which the startup can come up with. So what they need to do is that they say, we cannot work independently. We cannot be this third party company which is just sitting outside and wants all the data, because that's never going to happen. So what the idea is that we basically collaborate with the banks. We sit in meetings with them. We basically earn their trust, and we come to a sort of setup wherein we will say that we will be recruiting lots and lots of agents, each maybe one bank, one agent, and that agent could be belonging to that bank, or the agent could be belonging to the firm. So there could be various those kind of arrangements. But essentially, what we do is that we come up with one agent for one bank, which this particular agent, when that agent goes to the bank, will have access to the bank records. That person can explore all these bank records, analyze them, scrutinize them, go through all sorts of audit reports, and actually get a lot of learning from basically reading through all these various audit logs, and what all fraudulent transactions have happened in the past. But one thing is clearly prevented is that this particular agent cannot take any data out with him or with her. So basically that agent gets to access everything, but that agent cannot take those physical files or the software copies of that out of this particular bank. That agent has access to this data. It can that agent can learn everything, but agent cannot take whatever learnings is whatever the specific files are, that agent cannot take out with him or her. So remember that we are a consulting company for the world, right? So we don't want to be just depending on one agent. So we basically want to learn from all these various agents. So that's what we do. So there is a master agent who is going to be the master kind of consultant towards multiple banks. And what that master agent is going to do is that that agent is going to call all these various agents on every day for a meeting. And then in that meeting, every agent has to tell about what that agent learned in that particular bank. Say one particular modus operandi of fraud was actually very simple. It was something about stealing the actual CVV, or putting a keylogger or something, and getting hold of actual details. Maybe the second agent who comes in says, there was a slightly different modus operandi. There was a phishing attack which was first done, and then that was exploited. And maybe the agent 3 would also come in and say, we observed a completely different type of frauds here, because they just hacked some data from a third party where these credit cards were being used, and from there they basically attacked and did this fraudulent transactions. So what is happening in these agent meetings is that each agent is not telling each specific rows of the data which that agent saw, but actually just telling the insights which that agent got to see at that bank. And another thing which is actually happening in these agent meetings is that the master agent is learning about all this cumulatively. That's one good thing. But at the same time, each agent is talking to each other, and they're giving each other ideas of like, okay, when you go tomorrow to the bank, look for this kind of different modus operandi. And that's something which is very interesting, because on day 2 when they go, they actually are going with more knowledge, and they are also able to extract more insights from the data they are actually exploring at the same bank. And as these particular meetings go on and on, what happens is that this master agent learns a lot of details about how fraudulent transactions actually happen, but cannot pinpoint on which bank it happened, or it cannot really, this master agent doesn't really know about each and every row, or did not really see the data never left the source. But the master agent is able to kind of put together various things which happen for credit card fraud, and that particular master agent is the one who is finally driving this particular consulting firm which we had started as a part of the startup. And this operation which I just explained, right, where we have these agents and this master agent and so on, and the way it actually organizes agent meetings and across days, this concept basically is what is federated learning, right? So that's what finally it is. The model is not directly going and getting access to the data, but the model is learning from these various agents who are going and learning on that particular data. Okay, so before we go there, if there are any questions on till now what we've discussed, you can feel free to ask it in the chat.
Amogh, I have a question. This is Sham here. Can you hear me?
Yes, go on.
Um, I like the thought process that you can have a master agent,
Yeah.
but the way in which the master agent is going to capture the information from the other agents, when you don't have transactional data, you may want to cover in saying how will you minimize a bias or a subject matter expert not giving you there could be a bias on the subject matter. Okay. The pattern that is manifested in, let's say, a particular bank 1, bank 2, or bank 3, how do you know that that is a pattern that has been correctly captured by an agent, and hence that can be consumed by the master agent?
Sure.
It has to be an indicative pattern. So that's a broad level question I had for you.
Sure. I think when we get into the technical details of how exactly this master agent is learning, it will be much more clearer. And at that time, surely we can attempt to answer this question in a more technical way. So the next slides which I have are telling us the technical details of how exactly are these agents really learning anything, and what is this master agent in technical terms. So when we get there, I'll surely be addressing this issue of what about the heterogeneity of the data which is there at each bank, right? So yeah, we will get to that question. Any other question around just the flow in which this was explained? Okay. So okay, so this is just another terms what we tried to do when the data from a single source was inadequate for representing the real world demographic or diverse scenarios. That's the time we would consider federated learning. If we have all the data in one single place, those models will be much better. But the goal of this particular way in which we are building the models is to actually capture this diverse data or diverse demographic across multiple banks or hospitals as we go on. Second is there could be legal concerns for actually putting together all this data. That's something in which federated learning can come in handy. And the third thing is when we put all data together, maybe in the earlier ways in which we used to do machine learning, or the current ways in which we do machine learning, there's a huge risk which is associated with putting all this data together, and it could be misused, or there could be we have to basically have a very robust data security for keeping all this aggregated data safe. And to cover all of these things, federated learning can help, and it's a decentralized technique, as we just now saw. But let's get into technical details of how exactly does it work. Right. So what we do over here is that we basically have a coordinator node, like you can imagine that as the master agent, and this client node and data. And the client node basically is the bank, and the data is the bank's data. And the model which will be shared with that particular bank will be basically the agent who's going there. Right. So the first thing is that we start with the coordinator, like the master agent who is there. So this coordinator, and so basically before even we start, we need to have a network between this coordinator and each of these client nodes which are joining in. Right? So we have each of them joining in, and they are all connected, and they are connected to their respective data. And that's where we start. And it needs to be like, it's important to note that this is something which is synchronous. It's not something which is basically happening in one shot. It is something of a synchronous training. Basically, what I mean by that is that when this coordinator node is going to send an agent to each of these banks, is going to be simultaneous. So at the same time, this coordinator node is sending these models out to this client.
So is it a kind of this multi-party computation MPC?
It so basically this thing is not directly MPC, but it can be converted or executed in the MPC fashion in case we would need that. But by default, it is not MPC, because MPC would require you to have
the bidirectional communication.
Yeah, it's not directly MPC to start with, but there could be some few things in it which could be executed in the MPC fashion.
Okay, thank you.
Among the standard, the data that the model is expecting as input, you are assuming it to be standardized at this stage already, right?
Yes, that needs to be standardized, because each particular client node and the training loop which is going to happen is going to be same across all these nodes. So essentially, the thing is, as we go in these rounds, as we see over here in these steps, the coordinator sends the model out to the each nodes. Each node is going to do their local training with the data which they have. And essentially what this local training is going to do is that same model, the base version, which was basically, say, there are 10 layers, and each layer has certain weights and biases. So when there are 10 layers, and we have all these 10 weights and biases, suppose for simplicity, these 10 are the ones which are going to get altered when it goes and sees this new data in the local training which happens. Right? So basically each of these 10 layers are going to get modified according to what data that particular model is exposed to, and it's going to obtain an update from each of these client nodes. So each of these client nodes actually get updated. Now there's the same version of the model, but when it goes out to each of these parties, it's going basically and learning and getting adapted to each of those. And when that happens, that's basically what we call as the learning on that particular local node. And the round actually gets completed when all these updated models are sent back to the coordinator, and the coordinator basically has to fuse all these learnings together to produce a new version. Now that particular fusion, we'll get into the actual algorithms which do that fusion in the next slides which are going on, but essentially this fusion is what is federated learning as such. So from each node, we are going to get an updated model, which is going to come back at the end of the round. And that particular coordinator node has to now put all these models together and generate a new base model. So when we actually put it all together, we will get a different version of this model. Maybe each of these nodes would have pulled each of these weights towards themselves, but when it goes to the coordinator, it basically has to look at the bigger picture of around all these various nodes and put it all together and generate a new version. And this version again then goes back to this particular client node, and the cycle continues. So when it goes back, it again has to do the local training and so on. So essentially, for doing federated learning, it needs to be like lots and lots of like there are two layers over here of learning. One is the actual local learning which is happening at each node, and then at the end of every round, what that particular coordinator node is doing to fuse together all these updates. So that's the second learning which is happening. So it's kind of, your aim is to, in one way, if we go in a model centric way, the coordinator node started with one model version, and as the rounds progress, the coordinator node has the responsibility to see that the loss on, that particular data which is being tested, that loss has to decrease. And basically it's sort of a stochastic gradient descent, but in this particular, decentralized kind of way.
Yeah, question here.
Sure.
Yeah, so it doesn't seem to be too easy to make sure all your clients would have the same data schema. How do you ensure that everybody's on the same page, because you would need to have similar data structures for all your customers? And what kind of effort do you need to take to ensure that you get all the data into those schemas?
Sure, that's a very good question, basically. So first and foremost thing is that this particular effort need not be blind, because there are many trust factors which are coming in, and it need not be completely blind. It need not be that each node is like never interacting with a metadata network or a meta network wherein you can put together a few things. So a simple example could be like, you can pass the original schema of how the data should be in the first case. When we basically, before even starting federated learning rounds, what we need to do is that we need to pull together all these various, organize that the feature is like, so in terms of like the data, we refer to as two things. We need to have the feature alignment of these various data sets. So the feature alignment basically is the schema being same and so on. So feature alignment is something which we need to put in efforts and do. So the technique actually helps us to make sure that data never leaves the source, but it doesn't restrict us from doing all sorts of other ways in which we can actually organize this data to be consistent across multiple parties who are going to come in and do this. So one example I can give is that if suppose we are doing it between the data centers of the same bank who's working on the same schema, just because these banks are spread across two different continents, and we are legally not allowed to basically put data together. In that setting, the schema will be very similar. But in case when we are going to go across cross banks, like one bank being from one country, another bank being in another country, it needs that background work to be done before we even come here. So federated learning is a learning technique. It is not a full-fledged solution to start from the data itself. So the first initial bit needs to be done so that federated learning can happen.
Amogh, Sham here, just to add on to the previous question.
Yeah.
I have specific. So let's assume you did have the data schema standardized.
Yeah.
Now, depending, okay, let's remove the concept of a trust factor or the agreement. Let's assume we have agreement with each of the 4 or 5 banks. Now, the onus is on the bank or that specific entity that has the data to basically get it transformed into the standardized schema that is requested for the model, right?
It need not be like it need not be basically, it's a collaboration, right? So the bank is participating in it because it needs to, the final model is going to be useful. The bank is participating in this because it doesn't have the world's data. So
I agree. My question, Amogh, is not the elegancy of the design of federated learning. I don't have a concern. My question comes back to the point that when you're building the data, that you've got the schema standardized and you need to provide the input in that format. I'm just also saying that there's a lot of responsibility on ensuring that the unit of measure of that row of data, which is anonymized and not visible to you, but run locally on the bank's infrastructure.
Right.
Have you seen this work in reality? I mean, I've seen examples of code, but have you seen this work anywhere? This kind of architecture? It may be credit, it could be anything else. I'm just curious about that.
So I would tell you to hold your thoughts till some time, because I'm going to cover applications and I'm also going to cover real world applications where this has actually been applied, and we see a progress in terms of really seeing kind of effectiveness of efficacy of federated learning come alive. So it's yes, it requires work, but it's possible to do it, and it's out there right now, and there are many systems who are actually learning in this fashion. So I have some applications which we'll cover during the in the later half of this particular course, and you know, when we speak about specific applications, I think these few doubts which you have will get more cleared. Specifically about the way actually it operates together with examples and applications, it becomes much more clearer, and that's what we're going to take a deeper dive on very soon.
Amogh, I have one question
Hmm.
regarding the fusion of all the models. That is most important.
Right.
So can you just brief more about that?
Sure. Sure. So so that basically is a nice segue to my next slide, which is over here, where we're actually talking about these various fusion algorithms as we refer to them. So these fusion algorithms basically, so like a little bit of a history around federated learning is that it was started as in the basically the term was actually coined by Google when they kind of tried to apply it with their keyboard applications and in the cross device kind of a setting. And the technique where they had millions of these devices on which they wanted to learn, like this actual client nodes scaling up to really large numbers. They applied a very simple strategy and they called it federated averaging. So the first type of uh, algorithm which fuses all these models together could be just as simple as averaging the weights and biases. And this may raise eyebrows of a lot of data scientists who are who may just doubt that will averaging just simply work. But in the setting wherein there are thousands of such nodes, or even hundred thousands of such nodes, the averaging technique actually works very beautifully. And this another reason why averaging technique kind of so by averaging, what I mean is that each node is giving their suppose we are talking about neural networks, then all these layers which are there, those layers and their parameters are basically what are shipped up to this particular coordinator. So the coordinator has kind of the weight matrices across all these various nodes, and as a simple strategy you can just average it. So add up all these weights which are come across from various nodes and just average it by the number of people who have contributed, and you would get a new model. And this model has to be again sent back, again you will average, again sent back, and if you go for 400 such rounds, you eventually do get a very consistent loss being decreased, and learnings actually are very clearly visible. But of course that's the first kind of fusion technique, wherein what we wanted to really do was improve this main coordinator node, and each of these data points had like less number of data points, and you could essentially average the model out across many of participants. Another thing where it kind of works together, this iterative averaging technique, is also when the data is very homogeneous, sort of like IID or individual or like independent and individually identified. So the IIDness the data is suppose there, then iterative averaging kind of works fine. Federated averaging is kind of one level above iterative averaging, wherein we also take into account how many data points are actually there at each of these data locations, and we basically kind of normalize the weight matrices before we actually average it. So that's the second way in which we can actually combine and get the actual fused model. Another technique is the gradient average, and there are these are various papers which are actually implemented, which show with their results to actually say which method is kind of working for them and so on. So federated averaging, iterative averaging, these are sort of more common, and there are more many more fusion algorithms which are coming in. One by IBM FL is something called as Fed Plus, and the Fed Plus is actually slightly different. The Fed Plus doesn't aim to really improve the coordinator nodes model every single round, but what that Fed Plus does is that on each node it maintains a separate neural network, or the neural network which was personalized for that particular node. So what happens is that in the first training round, you would train on your data, and then you would give your updates back to this coordinator. coordinator would basically fuse it, maybe by federated averaging or iterative averaging, and pass you the updated model. Now, in normal federated learning, what you would have done by the standard federated averaging technique, you would have just dumped your learnings of that model and switched to the one which the coordinator node is giving you. Whereas in Fed Plus, what actually happens is that that particular node retains its personalized model, and it basically has a formula in which it says, I'll accept from this coordinator node only some insights. I can give it like some parameters like alpha, which can vary from, say, 0 to 1. So I'll just basically adapt certain insights from this model, not all of it, and I'll add those insights in such a way that I'll take, let's say I'll take 10% of the insights from this coordinator node, and I'll add that to my personal model. And what that's going to do is that it's going to basically, for each of these nodes, they can actually set their own separate alphas and so on. So what happens is that they end up getting different models on each of these kind of nodes, and that's something which is very personalized to that node, and it comes in very useful when there are cases wherein the data is very large. So suppose this particular client node actually has 10 lakh rows, whereas this other node has just 1 lakh rows, but there is diversity between this data point and this data point. So in that case, what you don't want to do is that you don't want to just simply average, but you just want to basically learn some insights from this node and add it to your model. And that's something which Fed Plus allows us to do. So that's just one example in which you can use the same federated learning concept, but develop models which are basically helping you improve your own model without basically accepting everything what the coordinator node is doing to you. So those are so that's what is called as personalized kind of federated learning. And the other setup is model centric, wherein the coordinator node basically was the main one, and that particular model had to keep on improving over time. Any questions on the fusion algorithms here? Okay, so Sham, maybe another way of understanding how that various homogeneous, or suppose there's a lot of data which is kind of very specifically tuned to a particular bank, how can that be improved? Probably Fed Plus is one of the answers there, wherein we can have a test data set to actually measure the performance of how that particular model is improving. And that test data could be basically assembled by basically working out some anonymized data which could be actually shared between the groups, or it could be just purely that particular bank's data itself, and we don't really care about what test data the other banks are using, but our whole goal is to improve that particular model which is only out there by that one bank. And the test data basically can be only that particular client node's data, and we can just keep using Fed Plus and see if there is any improvement in that particular on that test data, because we federated. And with that alpha, we can surely control how much of the external bias we want to really let our model be exposed to. So I can see a question over here from Akash. He asks, in Fed Plus, does parameter, example, this alpha get updated on the coordinator node? So this alpha parameter is actually a parameter only private to the client nodes. It need not be actually shared with the coordinator node. If we want, we can share it, but essentially the alpha is going to just tell how much of the global insights do you want to factor into your present insights. Whereas the coordinator node, the only job it has to do is whatever updates come, I will just average it. So the coordinator node doesn't need to really know how much insights are you really trying to learn from this global model which is being passed, but alpha is something which the client node is kind of controlling. Does that answer your question, Akash? So yeah, we spoke about federated averaging, iterative averaging, Fed Plus, and all these are all these are things which are more applicable to neural networks. And from my analysis, at least, I would like to say that the federated learning as a technique is actually much more popular with neural networks than other kinds of machine learning techniques like decision trees or linear classifiers. It's just kind of because of what the way in which actually it's trying to learn, right? So to average together everything, neural networks are the easiest to just put it all together. In case we want to do it across, say, XGBoost, then these are actually proprietary algorithms by IBM, wherein they have implemented XGBoost in a federated manner, but the way in which it actually operates is very different. Right. So in this particular call, we will not try to get in detail of how federated XGBoost works, but I would encourage you to read about the paper which is out there to understand how exactly that's to be done. Uh, Same ways, decision trees and so on. You can federate all these various other types of uh, models as well. But even across the frameworks, like these are some of the frameworks which are very popular in terms of doing federated learning. Uh, there is PySift, which is it's kind of funded by PyTorch, and PySift was one of the early implementations of federated learning, and they have a concept of remote workers and trying to get pointers out to a different system, and then trying to federate using those pointers. And essentially, it's the same algorithm but implemented in a slightly different way with PySift. IBM Federated Learning attempts a more straightforward kind of Pythonic way of doing it. And in the later half, let's actually try to see a demo also of IBM Federated Learning code and how that's to be done. Fate is another one. It's one popularized by VBank from China, and it's backed by Linux Foundation. And it has actually developed even further into federated learning by calling it, like, what we are trying to do over here is termed as horizontal federated learning, wherein the features have to be actually aligned across different client nodes. And VBank has actually invested in a technique called as vertical federated learning, or feature transformation federated learning, wherein they don't need the features to be actually same across different nodes, and they can still do federated learning with that sort of a setup. So that's something of algorithms which are actually implemented in Fate. Uh, and these are all open source. They are kind of free to go read the code implementations of all these various all these frameworks. Flower is a very upcoming framework. It's open source again, and it's kind of more towards this neural networks, wherein they call it strategies, and you're free to either use these available strategies, or you can actually invent your own. And it's a very nice interface to add your own fusion algorithms in Flower. And NVIDIA Clara is kind of they're taking it really seriously in the medical imaging space, where federated learning has really huge potential. And so they have actually invested into using their GPUs for trying to do this in a much more efficient way. And they have a Clara SDK which is available as a part of their NGC program to actually try out and build federated learning for medical imaging. As well as for other things, there are tutorials available for doing, using NVIDIA Clara. So, and you're free to use any of these platforms to actually take a deeper dive and get into the code level of how this has to be implemented.
Amogh, I have one question on fusion algorithm.
Yeah.
In Fed Plus, we are focusing on the personalizing the client node.
Correct.
And in general, we are improving the coordinator node. So overall, federated learning, what's the aim is to improve the coordinator node or the client node? Because there is a two diversion of here with respect to the Fed Plus and the other fusion algorithm. So it's based on the use case, like how it's like that.
Sure. So that's a very good question. Basically, yes, you are right. It depends on clearly on the use case. Like I can give you this example as we, go to the next level. I was just hoping we could take a 5-minute break before we continue onto these various examples. But just as a quick, an answer would be yes, it depends on the application. If suppose you have lots and lots of these nodes, and your priority is to not improve each of these nodes at a time, but your priority is to actually improve the model which you will basically. So imagine a case wherein you have a user base of 10 lakh users, and not all the 10 lakh are actually all contributing towards federated learning. Say only 10,000 of them are actually contributing, but you want the model actually to be deployed to all the 10 lakh. So in that case, what you would prioritize is you would prioritize the coordinator node getting better over time, and then you will freeze that particular model after doing some federated learning rounds, and then ship this model all to this 10 lakh users who are using it. So that would be one example in which our coordinator node is the one which needs to get improved. Whereas consider a hospital case which actually is doing, say, around 80% accuracy on its model, and you want to just improve that model by learning insights from this diverse data. You are confident 80% of the times, but you want to actually get it from 80 to higher number, and that's something at that time maybe you'll go with Fed Plus. So it's on the use case as well. So, hi everyone. With that short break, I guess we can continue with the applications of federated learning.
Amogh, can you hear me?
Yes.
Sorry, I missed your answer of the last question. Some voice, I because of my headphone is not working. Can you just repeat the answer?
Sure. So basically, it depends on. So it depends completely on the use case. Like for example, in case we want to really, we have say a lot many clients who are using this particular model, and we have just a subset of them who are contributing towards federated learning. In that setting, maybe you could focus on improving the coordinator node, and that's the one which is the most important. And so that's where you will use federated averaging alone. Whereas if you have lots of data on your client node, and you have just few number of client nodes, maybe in that setting you will go for Fed Plus.
Okay. Thanks. I got it. Thanks.
Okay. So, okay, let's go through some applications which will make it very clear how federated learning is actually being used in the industry. So, first application basically is the one which with which Google pioneered federated learning, and that would be the keyboard predictions. Right? So, what Google actually they've written a paper also about it, and what they try to really do is that they really wanted to improve the next word prediction model of their keyboard predictions. So, and so one main difference between the data which they could put together from all the internet, which is articles and various things, had proper English, whereas what users were typing on their phones was actually very customized to how each user was actually typing a few words on their phone, and it was following a different pattern. So they could always notice that the way to actually really improve the user experience was to get hold of that user data. But shipping all of that data onto the cloud would be it's concerning for privacy, as well as it would be just too much data to be collected from users. So what they did was that they came up with federated learning as such. They could sample a few phones, and so one thing very cleverly implemented by them was that so just having data on a phone is not enough, right? It needs to be annotated. And specifically for keyboard predictions, what you can do is that you don't really need always explicit signals for telling you that the data has to be labeled in this way, but it can also get hold of a lot of implicit signals as well, like did the user pick what was suggested, did the user pick something else, those kind of signals. All those various signals were put together, and they basically could get a scenario wherein the data was actually feature aligned properly. It was less amount of data on each of the phones, but they were like trying to do federated learning across like 10,000 or more than that number of phones at a time. And yeah, of course they did it in a fashion that the phone was connected to the power source, so that they wouldn't kind of harm the battery life of their users. But they essentially did it to improve their global model, which they were deploying to lots and lots of phones. So very few phones were actually being sampled for doing this learning, but every time, like, so say at every night, your phone actually used to receive this global model from Google almost maybe 300 to 400 times, and the training would actually the number of training rounds were 300 to 400. So you can imagine the scale at which it was actually working out. But what they could do is that without actually transferring the user data up, they could improve their prediction model. So that's one very successful application of federated learning, and of course they could scale it to the phone, to the photo and the photo predictions and those other vision models as well. And so they are currently doing it with their Gboard as well as their photo and all those things. So they have been documenting it on their site. So encourage you to, suppose that is a use case to consider. Have a look at how Google implements it, and that's a very good source. Another such mobile kind of use case is like, and mobile type of use cases are usually called as cross-device use cases. And because usually each device is not going to have lots and lots of data, it's going to have just that user data, but it's going to be diverse enough across users. So another thing is this other startup called Doctor.ai. They were in this space of pharma and clinical trials, and so they had some ML models which were trying to find out from a selfie, find out about your mood, or they had a OCR model which was working on a phone. They also had like this smart selfie and all these various other sensor data which was being collected on the phone, and they wanted to improve these models, and they did not want to ship all the data back to the source. So they employed federated learning for doing that. So these were kind of use cases wherein it was like a more mobile centric and less data on each device kind of a setting. And then we have these other scenarios wherein we switch over completely to kind of industrial domain IoT and a space of predictive maintenance. And this is something by Cloudera Fast Forward Labs, and actually they have a very nice web demo which explains all of these things in much better way. Let me just switch over to their web demo. Okay, so this is a very interesting way of understanding federated learning, right? So what we have over here is that we have a factory, and the factory has some turbofans, 4 of them or multiple of them that way. And so for every 1 hour when this turbofan runs, you make $300 in profit. And so every hour, $300 is what you earn. But in case any of these fans break down, then they basically cost $60,000 to repair. So these are very risky to for failures. So every time it breaks down completely, it takes you $60,000 to repair. But in case you want to just take it down and maintain it, that's going to charge $10,000, and it's going to take your 20 hours of time to do that maintenance. So you are running a factory and you're free to choose how you want to go ahead and maintain these factories. So the first and foremost thing what you and you're just as a competition, they also have some other factories which are very similar to you, and as a part of competition, you need to basically be making, I think, around $3 million to finally win this competition, right? So and each of them is going to apply a different strategy for doing preventive maintenance. So let's click on start playing. And the first thing what we try to do is that we basically just go with a corrective strategy. So we wait for things to fail. If it fails, we go and repair it, right? So we have 2 failures. We are fine to incur those losses, which are like $60,000 losses every single time it fails. And so that's a very risky thing, just waiting for things to fail as such. So what we do next is with something which is very, very, very popular, which is preventive maintenance. So you come up with a schedule saying after every 193 hours, I'm going to just do maintenance. It's also very similar to how we treat cars. After every 10,000 kilometers, you do the maintenance. So that's the strategy, which is preventative. And that's something which is going to, of course, be slightly better in profitability over the way of waiting for everything to just fail. So preventive maintenance is kind of good. You can also see your profits are kind of trying to be on the upwards. So, but this is a good strategy. It still doesn't use any machine learning yet, right? It's just purely based on what you observed, and you came up with a time to just maintain it. So next, what you do is that you have kind of enough data about these fans, and you can basically hire a data scientist to build the first kind of a predictive model. So what exactly will this model predict? The model actually is going to predict how many hours are left for this turbo fan. So it's just going to just put some sensors on it which tells you, okay, more 100 hours are left, or 200 hours are left, and so on. But in case the prediction model says that you have just less than 10 hours for this particular turbofan, what you would just do is that you'll take that and you will just call in for maintenance, and you will spend that $20,000 or something to repair it. Right? So you go in using a machine learning model way. So this is the local predictive way. This is largely how the current industry is working, wherein we can see that local predictives are very good. You're using your turbofans data, and you have some sensors on it, and every time your model predicts that's going to be taking less than 10 hours, uh, you're going to pull it into maintenance and do. And then basically you can upgrade yourself to this latest technique, which is of federated learning, wherein you are going to federate across the other three factories which were using the similar type of turbofans, right? With the same sensors, so the feature alignment is there, the same data is sort of getting generated. It's just that you are not moving that data across these factories. So when we finally upgrade to this federated predictions, uh, and now is the real game, wherein you basically see each of these other factories are switching to just a corrective. One is going corrective, another is going to preventive, then there is local predictive, and then there is federated predictive. So as you keep playing this game and in various combinations in the simulations, what you usually observe is that the federated learning strategy often, like not often, like almost every time outperforms the local predictive models. uh, Another way to just understand it is that instead of going local predictive and using only 4 fans data, you're doing federated learning and you're getting access to the insights from 16 fans. And that's what is really helping your model get better and better over time. So essentially, this is one way in which we can think about how federated learning can be really applied. And this is a very interesting way in which Cloudera Fast Forward Labs put it. And I found it very amusing to see that federated learning often comes up to the top and gets you the most amount of profits. Any questions about this example and the use case?
Question by Ashwini.
Yeah.
She's asking what is this? What is this you are running? So basically, I guess the graph that was there.
Right. So these are basically, so okay. So a little bit of background of what that is basically is that NASA had some time back released a data set about its turbofans and predictive maintenance of those turbofans. And so what Cloudera Fast Forward Labs have tried to do is that they have built a simulation using that particular data. So essentially, what the simulation we were running was, going across the timeline, trying to see if any of these turbofans are going to fail. So if the turbofans are running for, like, and the way to see it is that if they're running fine for 1 hour, you make $300 in profit. And if they fail, you have to pay $60,000 to just repair these fans. And if you want to maintain these fans, it's going to cost you, I think, $10,000 or something to maintain it. But you're also going to lose 20 hours doing it. So that was a very intuitive way of trying to find out which strategy would kind of work in a final way. Like corrective would be waiting for things to fail. Preventive would be getting a schedule to say after every 200 hours or something, I'm going to just go ahead and maintain these fans. Third would be using machine learning, which is every factory has just 4 fans. So over those 4 fans, you do machine learning and you predict how many hours of this machine are left, of this turbofan is left. If it is less than 10 hours, you pull it into maintenance and you use that as a strategy. And the fourth one was you basically collaborate with other 3 factories who also have very similar fans, and you use all of them together. Like you basically do federated learning across the 4 factories, and you improve that model, and you use that for actually doing your preventive maintenance. And that's the one which usually wins. So and it's an open demo. Everybody can you just use the link and go there. You can just type turbo typhoon or fast forward Cloudera Fast Forward Labs. I also have a link in the slides which I have prepared for this session, so you'll get the link there as well. Okay, so and then basically is like, let's just go back to the slides, and then there's healthcare, and we're going to talk more about in healthcare soon. So just to get a recap, what we are trying to do over here is to treat the data as oil, right? So data is powering everything, but there are hurdles about this data. So to get the best ML models, the data usually is siloed. It's siloed across organizations, across, even if you just want to put together all the data in one company, it's often across multiple business units, multiple geographies, and difficult to put it all together in one place. So those are one scenarios in which federated learning can help. And the second one is IoT devices, like many IoT devices generating lots of volume of data, and just that much volume being aggregated could be sensitive data which is being aggregated, and as well as just sending up 1 GB of data every single day is a very expensive thing. Uh, Second consideration is that when we have data together in one place, uh, you have to basically make that you have to have a robust infrastructure to protect this data which you're aggregating together. If you have to make sure that there is no adversarial use, there is no data leaks happening, as well as various regulatory challenges which you need to be kind of keeping track of. And third is actually, this is something which is one of the main reasons why federated learning is actually gaining popularity, is diverse data and capturing various scenarios is a real competitive advantage. And in the way the data business works is that once you sell any piece of data, you're essentially doubling its supply. So the data is sold, then you just lose your competitive advantage. So the best way could be to develop more into this kind of federated learning techniques and see if that is something which you can use to improve your models. At the same time, don't lose your competitive advantage. So with that, we can actually jump on to another demo which I have over here, which is going to be the code walkthrough of this IBM Federated Learning. So as I just switch screens, you can just ask your questions directly or via chat. So what I have over here is nothing but IBM Federated Learning GitHub code. So this is something which I have given the links as well. This is IBM Federated Learning, and they have some examples on how to do federated learning. So over here, the way they have packaged their library is something of a wheel file, and the current version is 1.0.4, and there is this wheel file which you have to install on your machine to actually get started. They have given some notebooks, and notebooks actually walk you through examples. So we can just go through, I've just gone into the specific notebook, which is going to show us a KDAS classifier over one of the most popular data set, which is MNIST. So this is basically, and they have some they have really nice documentation to actually get into how to do federated learning. Right? So essentially what they have is that they have a concept of aggregator, which is the coordinator which we were referring to, and each party is usually referred to this P0, P1, and these are the parties. Right? And they have this nice picture of what's going to really happen. So it's going to be the cloud aggregator and the parties, and then a few commands which they have this is the protocol they follow to do federated learning. And so the task at hand is the one to basically, each party is going to have a fraction of this data of handwritten digits. And these are I assume that most of us are aware of this handwritten digit data set, and it's a sort of image classification problem wherein from the image of a handwritten digit, we want to just classify which number was present in that particular image. So let's actually get started with the first thing here is that there is a generate data piece of code over here in this library. This generate data is basically, it's going to put together this data in a specific way. It's going to make some NPZ files out of it. But and I've already previously run it, so I'm not running it again. So on one party, this is party 0. It's going to pull 5,000 images, and we can actually see the distribution of from 0 to 9, how many samples were actually present in the test of in the train basically of these. So there was just like 200 points which I had pulled, and so these basically sum up to that 200, and the rest basically we just use for testing. And so the party 0 and party 1 is kind of simulated in this fashion here, and we can even just go through the examples, and there is a folder called data, and on the MNIST, we can actually see it has made two MPC files which are representing the respective parties. So data party 0 is the it's like the data has to be given as a tuple, a train and test kind of data tuple, which is put together in this NPZ file. So there is data party for 0, and for the party 1, there is a separate NPZ file. With that, basically, that's the first step. Second step is, what is this model which we are going to federate? So this is the architecture of the model. We can see the number of classes are 10. It's a sequential model with some convolutional layers, max pooling, and the final one is basically a dense layer which has a softmax activation. And so this is basically same as what model we would have otherwise built. So that remains exactly same. And so we generate this model, and this is the base model. So yeah, essentially the fusion algorithm has to be entered here, which is in this case the iterative fusion handler. You're free to go through the source code and see the other fusion algorithm implementations and also the other examples which are out there. So over here, these are the parameters. How many rounds do we want of federated learning? Like in this case, there are going to be 3 rounds. And how many epochs are going to happen on the actual the parties who are going to join in. So that's what is being defined here. And we just have to start this aggregator. And from a party, we basically need to have a very similar configurations which are telling where the data is, what is the data handler. So in case we have slightly different data handlers, that's something to be taken care of here. For every party, we can have a different data handler. Essentially, data handler needs to kind of pull the data from that particular party's database or data location and kind of do the feature alignment and give out the output which is basically consistent across multiple parties. And once that is done, then basically it just needs a little bit of what that model is and the protocol handler for actually doing the party work. Then it's just you're going to start this particular party and register it to the aggregator which was started in the other page. I'm going to do it the same for the second party as well. So then we can switch back to the notebook wherein we have the first aggregator, and we can see if how many parties have registered. So in this case, we see the number of parties registered is 1 so far, and we can just cross check. I think this has to be set. Okay, so we can see the 2 parties, both of them have registered, and then from the aggregator, we can start the training by calling the training command. And once it starts, we can just switch back to the party and see if there is any training happening. So here we can see that the 3 epochs have happened, and then the models were actually sent back. A second round of training has happened. Models were sent back. Third one is going on, and with the third kind of round, we are done with our 3 rounds. So I think we should get a message over here saying we finished global training. So the model is actually out here now, and we can try to plot it. Like this was something which was done for previous epochs, wherein we had a lot many number of epochs. We could have these long graphs, and so that's usually the way we can do federated learning using IBM Federated Learning. Any questions on this? Okay, I encourage you to actually go through their GitHub code and try these notebooks out. It's kind of very straightforward to get started with this. Let me share my slides again. Okay, so going ahead, these are like the banking applications which you were saying, IBM, VBank, they both have tried these various banking applications. The way, the first one is actually very similar to the way we just now saw. The data was actually spread across, there was feature alignment, and they could just do federated learning across the institutions. The second one was actually more interesting. So in this second case, what they did was that they basically for each of the banks, what they did was that they kind of built this graphs of relationships between various bank accounts and various transactions. And these graphs were what were used to basically get some, the graphs were used, and the weights on the edges of these graphs, these weights and the actual relationship between the graphs, those were transformed into features. And with that, what they could do is that they could get feature alignment across multiple banks. And with that feature alignment, they could actually then go ahead and do federated learning. So the federated learning bit was one part of the way they actually solved this financial crime detection problem. But what they really did was that they used these graphs to get to that common denominator which is required across all the banks. So it's a very interesting piece of work and a very good application of how federated learning can be applied in financial crime detection. Any questions on that? I encourage you to read through the papers to see how exactly that. Another example of banking would be VBank has also put out content of how to go about doing federated learning with financial data. So that also is quite useful to learn about how this is to be used in banking area. Next, basically, I can just take 5 minutes to quickly go through the persistent healthcare experiments which we have been internally doing for with this particular data sets and with libraries like Flower, IBM Federated Learning, and PySift. And what we observe. So the setup is actually very straightforward. It's like what we really want to do is that we want to get hold of diverse data set, and we want to do federated learning across multiple hospitals. So the first phase we actually took up is this endoscopy image classification, which has a huge class imbalance. So what we actually observe is that this is a very interesting data set. It's a real sort of real life data set. It's called Cozier data set, which has these endoscopy images, and they need to be classified into certain anatomical conditions as well as clinical conditions. Like we need to know where the pipe connecting the mouth to the stomach is ending, and so that's the positioning of where the endoscope is. The second part is actually all these around polyps and ulcers, which are actually marked and annotated in this particular data set. So what we did was that we split the data into three parties, and the way we did it was that we observed that the data is actually in three different resolutions. So there is a resolution which is like 576 by 720 resolution, another one which is 1024 by 1280, the third one is 1072 by 1920. And what we observed was that each class, there was kind of the 576 was so that image, in those images were actually there across multiple classes. 1024 was less in number as well as class wise they were less, and 1072 also were less in numbers, but they were actually spread across classes as we see over here. So what we did next was that we basically put it into three separate federated learning parties, and we federated over them, just the standard federated averaging. And what we observed was that the final model, even though there was such a big class imbalance between parties, the final model actually did really good accuracy as well as F1 scores. And then if we see confusion matrix, it's quite good. And this kind of gets more amplified when we see these graphs also are clearly showing the way across the rounds how basically the final aggregation model actually is outperforming the individual models as well as the loss decreasing. But if we had not done federated learning and we were just stuck to using that party's data alone for training it, we would have been probably around 0.7 or something with the 576 model. But the other models were pretty low. Like they were like in 0.4, sometimes in 0.5s, and pretty less. So even if we go with the confusion matrix, it's like you can see it's very like the final model actually has it behaves as good as a central model, whereas individual party models are all confused and they're kind of not up to the mark. And this is kind of scenarios which we observe in healthcare a lot, wherein there are some hospitals which have really good data sets, and there are some hospitals who have kind of very few classes with them. So with federated learning, we could actually work through healthcare and really improve their scenarios. So even the classification report of each party it shows out very clearly what really is observed out there. Just continuing with that is the second data set which we had was around polyps. And so here we basically had two separate data sets. One was from Norway, which were around 1,000 images, which were all annotated to tell where the polyps are. And we had another data set, which were from Spain hospitals, which had around 600. So as a setting, what we did was that we basically said we are, we assumed we are Spain hospitals, and we want to improve this model and find, how basically the accuracy of this particular Spain model can be improved by learning insights from this Norway hospital in a federated learning way. So we switched to Fed Plus, and basically observed like federated learning, we had a PSNR value of 16.5, and when we did federated learning from this quasi data, we improved it to 18.4. And clearly, as we see, basically, the data was actually across like different parties, but the PSNR value still increase, and just as a metric, PSNR goes from 0 to 50, so any small improvement also in PSNR is a big jump. And we tested it purely only on the CBC data, right? So it's like we tested it only on the Spain data, and we could see clearly that the Spain model was able to improve by learning insights from Norway hospitals. So this is the last slide I want to conclude on. Basically, is that there are certain thumb rules of federated learning. We need to find a situation wherein data is siloed and it cannot be aggregated. If it can be aggregated by, say, anonymizing or the other techniques which we can apply, and we can put it all together, by all means, you can do it, and you probably will follow a different machine learning way of getting there. Second case is in case you have IoT devices, and in that case, it's too expensive to put together all this data in one place, and that's where you can apply federated learning. And the third thing is that we need to have this sort of conviction that our data, our model will improve in case it gets access to diverse data. So if suppose we are content with the model, and we also basically know that the diverse data will not really help our model, then in that case, federated learning doesn't make much sense. But in cases wherein, like especially healthcare, wherein we know that we have not captured the real demographic, and we want to really get there, those kind of use cases are prime for federated learning. So with that, and in the last slide, some links of reading through. I would really encourage reading the fast forward report. It's a really well detailed report. The second one would be to understand, in case healthcare is of interest, the future of digital healthcare with federated learning is a really excellent paper. Do read that. And IBM Federated Learning also has a pretty good all put together. So these are the top 3 references I would recommend to read through. Of course, there are many more, such as Open Mind and so on, to read more about federated learning. So with that, we still have, I guess, a minute where we could just take questions.
Hi, Amogh. I have the one question. Okay, regarding the bias in the federated learning. So there are more chances which, like the base, since some of the nodes is more having some bias towards some data. So that bias is fused to the main central node, and that central node will give the bias to the all other node also as well. So what about the bias?
So actually, bias needs a bit of more study on, like, and there are some IBM papers on specifically understanding bias in federated learning, and I would recommend you to read through that. But the high level understanding is that what is happening is that, because the model is federated across rounds, for every round the model is going to get its weights averaged. It's sort of like there's an effect of dropout, or those kind of ways, which it's like it's very analogous to dropouts. So essentially, your model is first of all getting exposed to more diverse data and insights. So the first chances of picking all the bias from one particular node is already minimized. And the second level is, in case your data is really kind of spread across multiple hospitals, you probably would maybe need to prime those models first to basically get to a state wherein they can be averaged. So the idea is that, just because the data of a particular hospital has bias, first of all, it needs to be established if it does have the bias. With like the techniques which Dataraj mentioned in the last session, we could do all those analysis and figure out if bias is actually coming from the data, or how exactly is the bias entering, and we can figure out first what's the cause of this bias. And then the second case would be, even after your data is so unique that even after averaging, the section of neural network which is doing the biasing is not really getting if affected, then maybe Fed plus is a better way than the general Fed average, because in that case you're not really propagating your bias that efficiently. You are controlling it with the alpha which you set. So those could be my 2 cents, but I would recommend you to read through this IBM FL references and the papers to understand more in depth how this has to be applied.
Sure, thanks for the question, and it was a great session. But the links which you are saying, so where we can get the slides and the link which you are telling to refer.
So I guess Prachi will send these slides out to you. You will get these
Okay.
links from there.
Okay.
And yeah, that would be one. Okay.
Thanks.
Akash, I read your question about gradient average could be useful there. Yes, it could prove to be helpful, but it needs to be kind of, we need to figure out where the bias is actually arising from, and that would be a way of tackling it. Okay, I think we're on time. Thanks, everyone. Prachi, any notes?
We really look forward for the second session in this series that you will be conducting on 10th of May. So thank you so much. And as you mentioned, I'll be sharing the presentation and the resource material. You can just forward it to me and share it with the participants.
Sure.
Yeah. Thank you so much, everyone. I will be joining back next Monday at the same time. I will send a reminder to you on 9th of May. See you soon. Thanks.
Thanks, everyone. Bye.